Hi everyone. Welcome to this week's session of the Underhand Center. So we have in our meeting, West Johnson, coming from the Hecla Lucky Friday Mine. He's the chief engineer there. Lives at the corporate office in Garden.
You have to yell. Come on now.
Okay. I'll try post projection. Yeah.
Speak up. Wow.
Yeah. So he's a mining engineer by profession. He did his bachelor's and master's at Virginia Tech.
Go Hokies.
That's a problem with memorizing. Yeah. So he comes with a wealth of experience. He's been at Hecla mine for 12 years. He comes to showcase an innovation for one of the mining methods that they developed to improve health and safety at the Lucky Friday mine. So let's welcome West Johnson and we can get it there.
Well, I'm surprised how full the room is. I thought maybe just a couple students that, I didn't know what to expect. I really appreciate everybody showing up and coming out here. A couple surprise visitors that I didn't anticipate either. So good job on the advertising. Again, my name's Wes Johnson. I'm a mine engineer. A little bit more on my background. I did live in Colorado for a little bit and got to know Hugh a little bit in my time when I was working at the Henderson mine. And just got a lot of different things I've kind of done over my time in my career. And this is probably one of the things I'm most proud of is the new mining method, the Lucky Friday. Let's see, which button do I push here? All right, that one works. So here's an agenda of what we're going to cover. We've got an hour. I don't think I can talk that long. I probably can, but I shouldn't. So I encourage you guys to make this interactive. Ask me questions, stop me. We can talk a little bit about it. Some of my friends that showed up here are more interested in the blasting side. I've kind of geared this more towards the rock mechanics side, thinking that maybe there's some people in here that are interested on the mine-induced seismicity that we're trying to solve at Lucky Friday. But yeah, please jump in and we can answer some questions as we go. But as I like to do, and as Hecla likes to do, we start off with the safety share. And actually, I was with Corby yesterday. I'm taking the PE next week, and I did the review course, which if anybody here wants to get their PE, I highly recommend doing that course. And if I can't like form sentences or talk appropriately, it's because my brain is full of all kinds of stuff I never use. So, but one of the things we were talking about, there's a book that came out earlier this year called Challenger, and it talked about the Challenger disaster. And some of you may remember this, but 1986, a shuttle launch happened and ended in a catastrophic explosion and complete loss of life for the crew that was on board. So when it happened, before they even put the shuttle out onto the launch pad for launch day, one of the consulting engineers, I can't even say it right, Thickenall, was concerned about the temperature outside and the O-rings, in the fuel delivery system on whether those were going to be able to operate appropriately because they had never launched in Florida in 22-degree weather. So there was a concern that was brought up. NASA personnel said, we don't see any big red flags on this. We're going to proceed with the launch. And then during the launch, what ended up happening was down in here, and it's really hard to see in this picture. And if you're interested in this, I encourage you to go and look. There's a lot of literature about what happened. And then there's this recent book that just came out. But down in here, one of the solid rocket booster support joints here started to come apart. And as it was taken off, it resealed, and then the vibrations and crosswinds opened it back up, and leaking gases escaped into the back of the into the nozzle flare and ignited the whole rocket. So catastrophic incident, really just a sad story. But looking at what happened on the other side and what we can learn from this, normalization of deviance, and I actually took all these bullets from the NASA website on their safety share that they had on the Challenger explosion. And what they had said was the problem with the shuttle began with a faulty design. Both NASA and the contractor management first failed to recognize that there was even an issue there. And then once they recognized there was an issue, the decision to launch the Challenger was flawed. So organizationally, how does that bad news go up to decision makers that are trying to change things? It didn't really follow appropriate paths. And then what they found is that the safety organization within NASA failed to recognize, the issue enough. I don't know if I can get rid of this thing. I'm probably going to break something. Here we go. I'll try to drag it down. There we go. They failed to exercise the control as the organization to be able to stop the launch from happening. So there were a bunch of different markers. And in the book here, it talks about the engineer from the consulting group that really tried to push back and stop. And his whole career was ruined for what he did. And decisions were made not because of what the science was telling them to do. It was because of the political ramifications. And, if we don't launch today, we're already late. We're going to get in trouble. Those other pressures led to bad decisions. And the reason why I chose this as a safety share for this discussion is we tend to go into organizations, we work with teams, we work with diverse different people. And a lot of you are considered the smartest people in the room when you go in somewhere, which is great. But how do we communicate effectively to be able to share, hey, here's a problem, here's how we're trying to fix it, here's the risks that we have in front of us, and be clear about those things. And then also stand on those things. As engineers, we have an ethics that we follow about really trying to make sure that we're going to improve and take care of people as they're going through it. Catastrophic event. There were some of the smartest minds involved in these projects here, but still had really bad outcomes. So learning from those things is something we can do to improve ourselves and grow. There are some parallels in the story I'm telling about Lucky Friday, and so you can pick up on those as we go through it. But encourage you to read the book. It's a really good book. So changing gears to Lucky Friday. Here's some statistics about the mine. We'll get into the technical aspects of what the project of changing the mining method was. But one thing I'll bring up right here is you can look at our production. It was on this nice ramp up curve, and then we had a bad year last year at Lucky Friday. And that's because we had a mine fire, which shut down the mine for 6 months. So going back to the safety share, how did that happen? All those other things. We ended up seeing an issue. We stopped the mine and we only got about 6 months of production. But as you can see, there is a big ramp up in the production rate of silver. Lucky Friday is a silver-lead-zinc mine in northern Idaho. How many of you have heard of Lucky Friday before? So nobody. All right. Well, it's a long storied mine. It's probably in some of the textbooks you guys have gone through. I'm not going to spend a whole lot of time describing the mine. Yeah, this is what I'm most proud of right here is that cool Rocky Mountain sheep that we got that they say don't exist in Idaho. We got them too. So looking at the isometric, it's a deep mine. So this green bit here is the mountain, and this is the Lucky Friday vein. So in the Lucky Friday vein, there's actually 7 different veins in that system, and it's right underneath the shaft, the production shaft, the silver shaft. And the silver shaft extends down 6,000 feet deep, and the vein structure kind of wraps around the shaft infrastructure in that area. It's kind of this hook-shaped vein that goes, and it's controlled by faults. Everything in this area over here is quartzite. So think strong, brittle ground. In the 80s, they discovered this extension of the Gold Hunter deposit. This was mined in the 1800s. This down here was found in the 80s, and over the course of about 20 years, it was developed. And it's now the primary producing vein at Lucky Friday. So everything over here was idled in about 2002. Over here, we started production in 97. And by 2003, it was the primary production location of Lucky Friday. So how many of you have heard of Luffle? Nobody? All right, there's no narrow vein miners in here. So Luffle is the Lucky Friday underhand longwall mining method. And this was patented in 1986 as a mining method for Hecla at the Lucky Friday mine. And all it is it's actually pretty dirt simple. It's just underhand cut and fill is what it is. You got a ramp that comes down, you've got what we call a slot or the ore axis that intersects at the center of the strike of the stope. And then you proceed to the extents. When you're done, you backfill with classified paste, and then you mine underneath it. So the innovation at the time was nobody was mining underneath backfill. And Lucky Friday started that innovation. So developing the mining method, one of the things that, as we mentioned, Lucky Friday veins are quartzite, so brittle and hard. The Gold Hunter veins are more ductile, so they tend to break a little bit more and they crush instead of burst. So for a long time, we were able to accept the fact that we have a very high stress regime at Lucky Friday. We're dealing with mine-induced seismicity and mine-induced stresses that will crush out the headings. But compared to Lucky Friday, it was way better in the Gold Hunter. So as we started to mine, this is the mining front. This is an example of the daily geotech report that comes out about mine-induced seismicity. We would see these events that are happening right near where we blast. So really hard to see on the screen, but these are blast events. And then the red bubbles are actually seismicity that's happening. What we found is most of these seismic events are happening on structures, so faults within the mine. And you can also see a lot of little blue dots in these white areas. So this is a long section view of the deposit. So you're looking at Z as this direction, and we'll call it X in this direction. It's not really, but it's close enough. So you're looking east-west this way, and up-down or vertical in that direction. And these little white bits are areas that we didn't mine. So those are commonly known as pillars. So we got pillars in a highly stressed mine. Pillars are no good. They're bad to have. And every time we blast, the stress redistribution wraps around, and we get small events in these pillars, and they continue to make noise today. So the mining method cannot take care of the sins of the past. We have to manage those pillars no matter what we do. So that's something that happened, and we can't unhappen it. So we have to deal with the pillars. Looking at how we manage it, though, I've got all these words on the side. Lots of different things. We've got monitoring systems, we've got communication protocols like these pictures that we send out to the crews. And then we also have administrative controls. So like in the mine planning, if we're at the bottom of the mining front here and stope A and stope B are approaching each other, we would stop one stope so that you could complete one and move out of the mining cycle so that you could safely continue. Because not only do you get the pillars in the vertical direction, as you mine two faces together, you create another pillar. So when we look at the mechanics of this, and I'm going to get it way wrong, I'm just a dumb mine engineer, so I'm not a physicist by any means, or I would say I'm a very rough geomechanic engineer. I know that the rock bolts go in the holes that you drill. That's about it. So looking at what's happening in section, so now we're looking in the north-south direction. So we've taken that long section and we've cut it so we're looking in the cross section of the drift that we're mining. So when we're mining with the Luffel method, all the stress is right at our feet. So because it's a high stress, the floor is crushed from maybe some blast-induced damage and also some crushing from the stresses, but there's still these faults underneath us. And so as we approach these faults with our mining front, you end up creating an excess shear across that fault and you'll push it to slip. So we cause the faults to slip, which is what makes all the seismicity happen after gold hunting. And we can get events in excess of 2.5 moment magnitude. So that's kind of the condition of seismicity within the mining front at Lucky Friday under the older mining style, the Lucky Friday underhand longwall method, or just conventional rubber tired underhand cut and fill mining. So what did we do to try to address this? If we think back to the 80s, when we wanted to change from conventional overhand slusher stoping and overhand cut and fill mining to underhand cut and fill mining, what were we trying to control? Well, we wanted to reduce seismicity and we wanted to make sure that we had better safety for our miners. In the 80s, there were a few fatalities right before the mine shut down and implemented the new Luffel method. Really bad conditions to be trying to change the way that we do our mining. The other thing was, because of all the delays and rock burst and damage and other stuff, productivity was really hit. So instantaneous mining rates might be good, but when you have a long delay because your ramp blew up and you have to repair it, you're not getting your productivity anymore. So really trying to control that seismicity and then also trying to get our productivity kind of get there. So then cost targets, if you can increase your productivity, you can reduce your cost. It's like everybody starts to win at this point. We have a safer mine, more productive mine, and it's cheaper to mine. So when we went to the Luffel, we had these criteria. We redefined these criteria in the context of this UCB mining method, and it's the same as the Luffel method. There's no difference in terms of how we're trying to improve safety, improve productivity, and lower our cost. And for those of you that have been around a little while, I was also involved in a project for a mechanical mining machine, and we partnered with CSM to do some disc cutting technique. Same criteria. Actually, that project was going on at the same time as this project, and we were kind of at a race. Do we go mechanical mining, or do we go with this new blasting method to be able to change the way that we mine? What we knew is that what we're doing at, back up. What we're doing up here is not going to work at the bottom of our reserve down here, right? So you've got a whole nother 1,000 feet of, vein that you want to extract. If it's bad now, there's a power curve that goes along with how bad it's going to be at the bottom of the mine, right? All right, so here's another thing that was shared for those of you that went to SME and heard the talk that Chris Neville and Phil Baker gave. One of the things they jumped around about was we are 40 years into an overnight success, right? So this is not something that, you can just jump out there and innovate overnight. There's no magic switch. There's no silver bullet. It's hard work and dedication to the problem and continuing to work the problem and not give up, right? Until you find the solution that kind of gets you where you want to be. Lauren Roberts, our COO, a few years back, had said, the experience is defined as the sum total of all your mess ups. So every time you mess up, kind of put that into the queue. He didn't say mess up, he said something else, but you know where it's going. So looking at what we did with the underhand longwall, that was developed back here around 86. And then we started de-stressing pillars to try to work about how do we control the stress field around our mining fronts. So we were experimenting with de-stressing back in the 90s. And then here you can see we went over to the Gold Hunter. And as I mentioned, it wasn't this brittle quartzite rock anymore. So the rock behaved a lot better and we were able to produce for better part of a decade without really any significant drama from a seismic issue. About 2010, 2011, there was a significant seismic burst at Lucky Friday and really challenged the way that we have been doing things. So we put in a microseismic system here in 2013. The RDM, this is that mechanical mining machine. We started the initial development of that. And then here in 2018, over the course of about 3 years, from 2018 to 2020, we developed this new mining method. So looking at the face, this is what a common face looked like before the UCB method. So this is just a normal cut and fill face. Over here, you can see the UCB, which is underhand closed bench. Don't ask me how we came up with that name, but that's what we call it. I don't know why we call it the Luffle either. So Hecla's tried and true. We've patented this method as well. So there's 2 patents out there with names that don't make sense. So over here, this right here, it's hard to see in the picture again. It's all broken up. So all the ore is completely crushed. And so you can kind of already understand if you've got a solid face and you got a broken face, you can't carry the stress in the broken face. That's how we're controlling the seismicity. So what does the method look like? Here's like a little cartoon, very simplified. We've taken away the development aspect of it and just tried to look at, you know, we've got a solid portion on one area, and we've blasted it one portion on the other. If you look in the cross section, the yellow would be your open drift. And then this dark blue is the solid ore that we're trying to extract. We drill it with long holes and then we blast it and everything swells into our drilling horizon. So there's no bottom cut. So in a seismic or in a highly stressed mine, if you were to put in a tunnel down here, that thing would crush out, right? Part of the reason why we're mining underhand at Lucky Friday is if it does burst, we'd rather have it blow up at our feet instead of over our heads, because gravity don't quit, right? So let's have it blow up at our feet. So once we do that, we muck out the swell, and then we just muck out we just advance on muck bolt through the broken rock until we get down to the next drilling horizon. So we've been able to condition 2 cuts. And it sounds pretty simple in this little diagram, but I will tell you that for about a year and a half, we would only get 1 cut. And then we would have this rubbleized big boulder field on cut number 2. That was just a nightmare. Looking at the blasting guys nodding. Yep. You know, you go in there with we started with 2-yard loaders and they don't really have any kind of digging strength. So a 2-yard loader going after, you know, a rock that's as big as that door, that's kind of cemented in there. That builds character, I think. So,
In chiropractor businesses.
Exactly. Yeah. They're not, you know, those 2 yards are not built for comfort. I gotta sit on a booster seat to fit in one of those cabs. I don't, my knees hit anyway, not built for tall people either. So this is the same kind of picture we were looking at before. And what's happening in this one is as we drill down into the solid rock with our UCB, these 2 cuts that we're drilling down, we're now actually drilling across these faults that we were creating excess shear across, right? So now we're going to blow up the fault along with our production blast, and we're doing it over a pretty long strike length. So we were looking in section on trying to do this. So how, if you look at the extension in the dimension, how far are we going? Well, we're blasting about 300 feet along strike with these shots. So somewhere around 30,000 pounds powder in the blast. So powder factor is also pretty high. As the guys at the mill like to say, it's ladies' milk when it goes through the crusher. Crusher's just making noise. It doesn't have anything to break.
Most of the riders like to say that too.
Yeah, exactly. So So it blasts everything up, but it's a pretty long strike length. One of the challenges, and I don't really have a slide on it, so I'll talk about it here, is how do we time that and how do we get everything to progress? The first ones that we did, we put the slot over here. Not really a slot, it's more like a burn that we're shooting. So we put the burn on the backside and then we blasted. Well, what ended up happening was we came into a huge hole in the stope and we didn't have any rock to put in it. So then we flipped the pattern. So now we have the rays over here and we blast. So this shoots straight up in the air, kind of opens up, and then all the production rings just kind of fall over, almost like, kind of shuffling cards. They just kind of stack on top of each other. And then you're left with a little bit of void on the backside. So another weird thing that happened with this is, that's great, we don't walk into a hole in the ground. Well, when we muck out the swell, when we get to right about here, there's a huge slug of blasting gases that never got swept. And so that was another issue. How do we solve that? And all these things were really solved by the miners underground. They started carrying a compressed air line that they put in and bury in the paste fill up above them. And then at the drift axis, they just crack that at the end of a blast and they create a pressure differential to push all that stuff out. Because blasting gases are heavier, they sit in the hole back over here. So kind of interesting challenges that came after that. Another one I'll bring up here, and I won't talk too much more about it. We'll get back to this fun stuff over here, is when we backfill in here, we use this paste, right? So it's about 30%. No, it's about 70% solids, a little bit less. It's not a true paste. As we put it in there, it's a classified tailing, so it's almost like a cemented hydraulic fill. So as it goes into the stope, all the cream settles out of the paste fill and it goes down into all the broken rock. So how do we prevent that from actually percolating through? The first couple of shots that we did, we found the whole face concreted and we're drilling this rubbleized, nasty face as we were trying to get things going. That was really focusing on how do we do our preparations before we pour the paste. So getting some fines in there, packing it down, spending more time on trying to get everything prepared before we put paste in there really helped control that a bit. So we kind of understand how things are going. So what's the effect on our seismicity? So I'll have you focus on the circle over here. These different little blue lines in here is the cumulative energy release, so in megajoules. So this is how we kind of track the amount of energy that's in the system at Lucky Friday. So we have a model, we have an empirical value on what we think it is, and then we measure it, and we try to look at how much energy are we actually releasing through seismicity. So when we look at this curve, it flattens out as we start doing this UCB. This is prior to doing the UCB, and then we did a whole bunch of shots all at once. So when we were doing the Luffel method right in here, what we found is a whole bunch of events that were happening outside of our blasting window. And so we were getting large events, so large energy events happening at what appeared to be random, right? So that excess shear on the fault, we don't know when it's going to let loose. We don't know if people are going to be in the stope. We don't know where they're going to be. And this is a common thing you find with seismically active mines is this re-entry time. It's a big deal. It's just like when you're blasting with powder smoke. When you're blasting at mine-induced seismicity, most seismic mines have a protocol on when you can go back in. How do you control the re-entry so you can go back to work? And it's based on the geometries that you've created, the mining rates that you've been undertaking. If you slow down your mining rate and speed it back up, and this applies to coal mines, applies to block caving mines, applies to, some of the Sudbury, mines that are, Kid mine, they have the same kind of things, but anywhere where you're going to be creating seismicity or the rock is breaking on its own, you have to kind of think about when do I put people back into these areas. So this was really hard for us to get a handle on, but then as you see, as we matured and got better with our UCB blasting, all of these bubbles start to line up with when we were taking those next shots. And so really the X's and the O's are in alignment. So here's one that doesn't align. Here's another one that doesn't align, but X's and O's are all lining up here. And we're seeing that as we progress, it's all kind of coming together. So it reduced. The other thing that was really interesting is, and Mark Board had to explain this to me about 6 times, so I almost got it. Probably 3 more times I'll be there. Energy can be released in lots of different ways. Heat is a big one, right? What's another one? Anybody?
Vibration.
Seismicity. Seismic energy as well. And can also be in crushing with the rock. So you have all this kinetic energy that's being released. Largely what we replaced with some of the seismic, we gave it all the displacement it needed. So it actually moved. And so we had energy being released with movement instead of it going into bursting the rock by movement and excess stress that's bursting rock, right? So a rock burst can be explained by a release of energy, and then you have resisting forces that are forcing the rock to burst, right? So if you think about it that way, the reason why we don't have this line at this steep angle here is because we're still releasing the same amount of megajoules. It's just the only thing we're measuring on this is the seismic energy release, not the rest of it. We don't have the energy release from heat. We don't have the energy released from displacement. Those are missing on this chart. So I found that really interesting. So if you think about Richter magnitude, Gutenberg-Richter relationship, if you want to drop the B value, if you can release energy outside of seismicity, that's how we've done. So looking at modeling, how we tried to model all this goes back to that stress relationship right at the bottom of a cut, or pushing the stresses down. And this ESS is the excess shear stress and how that's being interacted on. So Matthew Armanis, our chief geotechnical engineer, did a PhD on all this, and I stole all of his notes. So we'll move on. So one of the other things that we see is the re-entry time. And this chart is trying to show the amount of seismic energy. So this is average number of events per hour, and looking at how many hours after our initial blast and how many events are happening. So really the curve I would draw your eye to is this yellow one. So within 2 hours of our blast, we're up here at near on 100% of our events happening. So there may be 90, 95% of the events after the blast are all occurring within 2 hours of the blast. And then this blue line right here is the percentage of total events. So you can see also down here, we're only at 35, 40% of the total events that are happening, but the big ones are happening over here, as we like to say in Virginia. Get all the big ones out of the way, and then they can go back to work. All right, one other thing I'll call on this one is this guy right here. So we got this is 1 shift after the blast and 2 shifts after the blast. We're on 12-hour shift. This is 3 shifts. With the Luffel method, we were having to wait up to 48 hours in some areas to be able to re-enter because of the amount of background events that were happening, stress redistribution, then all of a sudden we'd have another event. So there's a regression, I guess, that was done by Amori, and you can do this at any mine really, that has seismic data. You can look at re-entry protocols based on that Amori principle. I don't know the math on it, but that's what we were trying to figure out, is what's the predictive time that we could re-enter. All right, so I'm going to come off of seismicity and talk about some of the other things that we had to figure out. One of the biggest things that changed with doing this new mining method is our production geologists could no longer go to the face and say left, right, left, right. Oh, you missed the vein, go left. Oh, missed the vein, go right, which is a big part of narrow vein mining. We want to be very selective. We want to be in that vein corridor at all costs. That's where we make our money, right? Well, we were going back to looking at this blue line is what our geologic model looked like. And if we had followed that with our planning without doing any more drilling, we would have been out in the woods. We would have completely missed the vein in this area. So what we entered into was pre-production drilling in advance of the mining front. And so Lucky Friday, being a very well-behaved vein, it's pretty long strike length, like 2,500 feet long, bunch of different veins. They all kind of stay in the same place and they go to the center of the earth as far as I know. So very persistent, very well behaved. Everybody says we know what we're doing. We haven't been drilling for probably a decade and a half or something like that. So this was a big deal to set up everything for core drilling when we had not been doing any core drilling. We went from 0 feet a year to about 100,000, 150,000 feet a year of drilling. Had to process it, had to log it, had to put it all together, figure out what scale of logging we need to do. For all the geotechs in the room, we had to kick them out so that they wouldn't try to do RMR on everything. And it was a big learning curve for the technical staff. So at the time, I was the technical services manager and trying to get everybody focused on, hey, we got to make sure that we can get the ore body variability and the program planning figured out. Where are we going to move that drill next? How do we try to get everything kind of producing this core, just like we're producing ore out of the mine, because it tells us where to go. So at the time, operations had this great new mining method, and they're producing, you know, at a fast clip. And the guys drawing the maps and telling you where to go had no idea how to be able to get ahead of operations. So operations is out here waiting on engineering. And if you ever worked in industry, that's a horrible place to be. You get the foreman, you've met Byron Bratton. You get him sitting in your office, pulling up a chair. He's about as tall as I am, maybe a little bit taller, but he's about 3 wider. If you ever need help in an interview, you have Byron just come and sit in. He's great. So pre-production detail, I'm not going to spend a whole lot of time on this, but really, you know, the more you drill, the more you know where things are going. And so we came up with it's actually really tight spacing, about 25-foot centers for the drilling. Some areas where we're more confident, we might go to 50-foot centers, but 25-foot centers for a lead zinc silver mine is really, really tight drilling. You only really do that in gold mining. But this is what's enabled us to figure out where things are going, helps us know what the grade, the thickness, and the geometry are. And this is my example that I gave our board of directors. Why do we need to spend so much money on drilling, Wes? I said, well, look, if I don't know where the vein goes, I'm going to drill this UCB blast down. And then when the miners come in, they're going to be slabbing that right rib the whole way down the strike of the stope. If we do the drilling up ahead of time, I'll know where the vein is, and I can steer my holes right into that corridor. I can blast it, and we don't lose any time. Our understanding where the vein is, our planning is all now representative of what's in the ground, and we have all the information we need to make decisions. So we got to go back and take a look. When we execute and we learn something, we got to come back and modify our drilling. We got to modify our geologic model. We got to modify our detailed design. These processes where you plan, do, act, you always got to put that check at the end. You got to check your work and go back and modify your process to make sure that you get it right the next time. Again, experience, sum total of missing the ore and having Byron sit in your office all angry. So I think this is my last slide. One of the things that we learned as we were going through this is it takes time for us to get results from our blast. So we blast, you walk in the stope, you see all this rock that's taking up the whole tunnel, and you're going, we did it, it's great. And you muck it all out, and you put your cement in there, and you try to go underhand, you realize that cement went right through the floor and it glued everything together. And then you go in there and you realize that only half the blast really pulled, and you're digging into like hard rock and you're having to blast your way through. Getting those parameters right is not, there's not a reference manual or something that tells you how to do it. So trial and error, and that comes to the fail fast. You know, we spent a lot of time on the burn patterns. We did everything under the sun. I don't know if the miners at your mine are the same as mine, but it seems like every jumbo operator has a special way that they like to drill the burn, and it's guaranteed to come out perfect every time. Except they never load the holes, so there's always a convenient scapegoat in the blasting crew. And then the mining fleet, I mentioned earlier, 2-yard bucket. It's like trying to eat a steak with gums. You know, you can't ever get purchase and try to pull that out. So we made a decision to widen up the stopes to a minimum width for a 3-yard to get more digging power so that we could produce a little bit faster. And our productivity paid for the dilution that we're doing. So we did those trade-offs to be able to make sure we make good decisions. New method, new tools. Lucky Friday's now using bulk emulsion. Prior, We had plenty of people trying to sell us on it, but we didn't have a use case. Now we do. Getting that. We don't have that many working places at Lucky Friday, so there's 5 stopes in operation. All your ore to feed the mill has to come from those 5 stopes. So when they are not producing ore, so when they're down for backfill or down for drilling and loading and all that, anything to speed that process up is gonna be money in our pocket because we can feed the mill. So that's the big focus of this mining method. We also changed our mining software and our planning workflows, design workflows, approvals, all that stuff. We went from engineers being on site 4 days a week to now 7-day coverage for planning engineers and geologists. Never been done before Lucky Friday. It was never needed, right? The miners are smart. They can figure it out. Well, if you blow everything up and it's all broken, it already happened. You can't put it back together and say we should have gone left. And then here, maybe this should have been at the top of the list. Safe production pays. We really focused on the seismic issue. Really, when I was working with Mark on the front end of this and we were looking at the mechanical mining machine, it was really about reducing the seismic risk to the mining workforce. Production was not the target. It was not about trying to feed the mill higher or get better grade or trying to reduce our costs. It was, how do we mine the next 1,000 feet the right way with lowering the risk to our workforce? And that drove all these other changes that we did. And I believe it, it really did pay off to kind of have that focus on, we understand that what we're doing is not going to work, 5 years from now. We need to put ourselves on the track that's going to be better. So we're still a seismic mine. So we have pillars. We have things that we did in the past that we can't undo. And we still have to worry about those things. We still have to worry about how we're developing. We're going into unknown regimes of stress as we go deeper in the mine. So right now they're mining at, I think, the 6,800 mine level. So that's about, it's almost 8,000 feet of cover where they're working right now. And we'll be going down to close to 10,000 feet of cover at the bottom of the reserve. And it's going to change drastically as we go forward. So if you guys ever go work for Hecla in the future as rock mechanics engineer, you'll be the one trying to figure it out. I think that's it.
Thank you, Wes, for the insightful presentation. Any questions?
Hi, Wes, great job. I don't know whether I'm asking this sensibly, but the energy released can be because of stress concentrate in the rock, and it can also get released on faults in the discount. Do you have any understanding how much of that energy is getting released in the faults and how much is getting released in rock failure?
I have an opinion.
Okay.
Our observation, what we've seen is it's not strain bursting, so it's not mostly coming out of the rock. I'd say 90% of it is coming from the fault slip. And even where we have the remnant pillars, I still believe it's fault slip that's really creating the larger size things.
Okay, so related to that, you haven't said anything about water. And effective stress rules on fault slipping for the most part. What's going on with water?
Too tight, can't come in. We don't have it.
No water problem.
It's a dry mine. Now, the star mine, about 3,000 feet away, wet mine. Somebody was talking about trying to connect the two, and I was like, that's a dumb idea. Don't take a dry mine and make it a wet mine. Don't ever do that. So, but yeah, Lucky Friday is mostly a dry mine. So we don't see that. Mark Board talks about his times in South Africa trying to do water injection along faults and stuff like that and induce. We don't have the water, so we don't really see those issues. But they're really smooth faults. I mean, the ground is so tight that when you're looking at the wall, you might think that it's just a joint or something like that, but that's actually a fault that's very persistent and it runs quite a bit. So it's hard to pick up on the faults when we're field mapping. And then now that we're blowing the snot out of everything, the damage on the ribs means it's even harder for us to figure out where those faults are when we're crossing them.
Thank you.
Yeah, good question.
So you're still using the silver shaft, and that we have another shaft, the line shaft going down.
So the silver shaft, yeah, actually, we just finished George's project. I wish he was here because this was what I was going to heckle him. Is that in 1980 he started the silver shaft, and then 2023, we finished it. So we got the surface hoist put into the silver shaft. It's the last piece of scope that was removed from the project. Silver shaft goes to surface. We have the number 4 shaft that starts on the 4,900 mine level. It goes down to the 8621.
Is that the one that was analyzed by Gabe Walton and other people here?
Yeah.
Because we had a research project where some of the faculty got involved in trying to understand the stress redistributions and how you can't make a circular line when you have those stresses.
Yeah,
Goes
so
oval
four
anyway.
shaft was a circle, right? And the stress regime is 1.5 times in the horizontal to the vertical. And then in plan view, it's still anisotropic because of the bedding in the rock. I think it's even worse in the horizontal plane. So we made it a football.
Yeah.
I think the teams here, mines helped us with that research.
So I'm curious what your dilution, average dilution is right now, and what's your minimum mining width?
Minimum mining width is, I'm going to say 10 feet. We're averaging probably close to 11. The pay zone in the vein averages around 6 to 8 feet. So 30%, 40% dilution. But the vein's getting richer as we're going deeper in these areas. And so we're still averaging a grade of about 13 to 14 ounces per ton. So it's still pretty good grade.
What's the sleep time, like, I guess, from the moment the first hole blows until it gets fired?
We don't sleep anything on purpose. We have slept them for like a shift or something, but for the most part, it's just how fast can we load about, 600 volts. So, usually it takes about a shift to load it out. We can get it done in about 12-hour shifts. Sometimes it carries over when we're doing like a double blast or something like that. We might end up, might take 3 shifts, 4 shifts, but again, we're not wet mine. And then the seismic, the only concern is the seismic energy that's in there if we're gonna see something happen. One thing that was interesting is because the holes are so close together and there's no bottom, we did have, the detonators crush. And so, well, you guys are nodding like, oh yeah, everybody knows that. We didn't know that. So because of the overpressure from the booster going off and the holes going off, the caps inside the adjacent hole boosters would smash and crush. And so now we have boosters with like a steel lining in there to protect the cap so it still initiates. But that was something our drillers actually found. They were down in the next cut and they were looking at the rib and they saw a live booster and everybody lost their mind. Yeah.
They should.
Yeah. Another thing to mention, regulatory environment matters. So here in the good old USA, we could do this method, but if you were in like Quebec, there's pretty strict regulations about drilling on top of patterns that were previously blasted. So check your regulations. I don't think we can apply this at our Quebec mine because are you drilling on top of another pattern and do you have a risk? You can offset it as much as you want, but have you measured the holes? Do you know exactly where they're going to be? And the pattern's like 3 foot by 3 foot. So 3 foot and then you're going to drill down 30 feet. Yeah, I could see it going over into the next ring, so just got to be really mindful about the environment that you're working.
What hole diameter do you guys drill your production?
3 inch.
With all these additional, caretaking, what type of mining costs?
I'm gonna say it stayed pretty flat. It's not really increased, maybe 5% or something more. But I would say it's not the mining method that's driving that. I think it's more the support systems to run to the bottom of the mine. So we're ever growing, right? Going deeper and deeper into the bowels of the earth, and it costs more money. So that height factor or depth factor that we have to the mine, I think drives our costs more than the mining method. There was a hope that this, because it's a lot more productive, that we drop our cost per ton, but we haven't really seen that because you still got to muck it out of there. So your support crews are just as big as they ever were. Loading out one of these blasts still takes quite a few people to do it. So
You also have the ventilation issues, right?
we
We have heat.
have heat. I wouldn't say we have issues right now. And actually, Justice Dean, he was up at Stillwater. He's consulting for us and helping us out with improving our refrigeration systems. But Lucky Freddy's a hot mine. We've got a expansive cooling plant there that has, I guess when it's fully built, it will be able to supply 2,000 refrigerated tons cooling to the mine. So
So 80 degrees, or what temperature?
our target temperature, well, the rock temperature in the ground is about 140, 130 degrees. And then we cool it down to about 85 degrees, 90 degrees. And then we have all these heat protocols around working in hot ground. So coming off the street, you wanna go work Lucky Friday, be a miner, you're probably not gonna be in the stopes on day one because you probably drop or cramp up. You have to get it acclimated to the hot mines.
So is there any thought given to, can you do anything on de-stressing or advanced stressing, in conjunction with, exploration with advanced drilling?
You know, So if I go back to that picture of,
If you did water injection, I know you don't like water, but
well, if we're adding it in there, I mean, we can control how much goes in. You need to just go, there you go. I'm gonna go back to my long section here. These areas right in here, there's still silver there, right? So those are the other questions. How do we go back and take out these oopsies from the past? And those kind of technologies, de-stressing and building a shadow curtain or something like that is probably the way to do it. I don't know, there's some, Mark has all the information on it, but there's some big nasty faults that are running right through the middle of that building. I don't know that, I think we want to take everything else out first before we come back and, you know, try to pull the last piece of Jenga out, you know, I don't want to be that guy. That's right, hopefully I'll be retired, that one of you guys can do it.
pillow robbing robots. That's what it is.
Well, that's a dumb question. Obviously, like if you were to try and mine through the paste on top of it and then deploy the same thing you're already doing, like it'd be a similar scenario to what you're doing everywhere else, but that's would have obviously been thought of. So what's the negative impact?
You could do that, you could come in the previously mined areas, either mine directly adjacent where you're in the stress shadow and come across and be able to drill down. It just,
Too costly.
yeah, it's just the payback on it. I think that's really what's driving it is we keep on crunching the numbers on it. When silver matches gold again, we get a 1-to-1 ratio all day long.
Wes, do you see much influence as the vein gets off vertical and your stopes are offset, that they behave differently than if you were have more of a vertical?
Like I said, we got a special kind of vein. I mean, it's 85 degrees all day long. It doesn't really reverse dip or change. We get some fault offsets. So what I showed in that other picture where it was kind of looking a little jog like this. This is where the geologists don't model faults very well, right? So there's a fault right, or there's an offset fault right here. There's an offset fault right here. And the middle does something different than what they drew. Right, so the middle's probably more in line with these other ones, it's just that offsetting fault. Yeah, that's another good lesson for everybody in the room. Don't believe leapfrog, doesn't connect the dots. There's something in there, it's probably an offset. Computer's not right.
Might be a dumb question. That large fault in your pillar. And maybe the pressures are just way too high at that depth, but consideration of epoxying the fault or grouting it instead of de-stressing it when you want to rob that pillar. They do it in tunnel construction somewhere.
You're holding back the whole world with that. I don't know you can stop it.
It's a lot.
This is different.
This
This is different.
We need a new type of epoxy.
I don't think, I understand what you're saying. I mean, even if you could pin it, if you could drill it and try to pin it, you know, mechanically try to arrest that movement. That fault could generate probably a Richter 4 magnitude event. That's a lot of energy. I don't know that we're holding it back. And then the slip area that you're talking about is maybe, I don't know, 2 feet or less. You're talking a very small slip area and a very persistent fault. So you'd have to, there's a lot of glue. Again, you get silver up to $2,000. You might be talking, we might find a way to make something happen. Although I think there's a lot of other mines in the valley that would come back online first.
What kind of daily production and where do you get your fill from?
So daily production rates at Lucky Friday right now are about 1,200 tons a day. Historical before this was about 800 tons a day. So we've had a pretty significant increase in our daily production, and then everything is classified mill tailings. So we take the coarse fraction and push it back underground for backfill. We used to go through these big, we call them sand cycles, right? So you'd have 8 places in production, and then 5 of them will go down. They all need backfill all at the same time. And you'd only got, 3 producing stopes at 800 tons a day, and you cannot make enough sand. And so we go into a sand cycle, and our friend Doug Bear would complain and say, nothing I can do, it just happens. But with having this be a more repetitive and fast mining method, we don't see sand cycles anymore. They're essentially eliminated, so. That's really good.
You know, it's really cool, because think just 20 years ago, when you did double breast backstroke, conventional mining, you have, in order to keep 1,000 tons a day, you had to have 30 stopes.
Yeah.
You had the ability to have 5, that's outstanding.
Yeah, we didn't talk about it, but Lucky Friday used to carve up the vein into like 200-foot high blocks and about 150-foot long, and be all these different blocks. And then you'd have a lead miner that would bid into that stope, take his crew in there, and they'd be jackleg and slusher mining in, timbered raises. Our friends at the Galena still do it. I don't know if anyone else in the US that, maybe there might be a hobby mine in Colorado that does it. So. Maybe, but there's very few that are actually raised miners anymore. It's the risk profile is not very attractive. You gotta be very highly skilled to be able to do it safely.
Where do you send your product to get refined?
We go to Trail, so Tex smelter just across the border in Canada.
Is there any place in the US you can get it done?
No, they killed the smelter in Smelterville in the 90s. And Doe Run got rid of their smelters. Maybe you go to Mexico? Canada's so much closer.
So when you think about critical minerals and value chain, it's hard to get domestic production.
What else you got? Something hard, come on.
How's your accident record?
What's that?
How's your accident record?
Well, we've done really well. So, last year, I think we had our lowest AIFR that we've ever had a Lucky Friday under full production. And I think it was right under, it was just under 1. So it was like a 0.8 or something. Yeah. Which is for Lucky Friday, it's crazy. And, one of the things to remember in that metric is most of the number on the divisor are people actually doing the work in the mine. Like, we don't have a whole lot of overhead. We don't put our corporate into the denominator or any of that. So it's a pretty honest figure. Really proud of that.
Well, if you ever want research done on epoxy that will hold the fault, you should come to Colorado School of Mines. We're also very interested in mine tailings. So if there's any issue on tailings, we'd be happy to partner with you.
All right. Good to know. Well, thank you, everybody, for your time and.
Well, thank you for the insightful presentation. Thank you all for coming. We'll meet again next week. Thank you. Thank you. Thank you.
I'll let you push the buttons.
Thank you very much.